So in section 2.3, we learned a particular method for being able to solve a second-order differential equation. We learned actually two. One of them was to turn it into a system of first-order differential equations. The second one was actually doing a little bit of a lucky guess. And if you remember, we came up with two solutions for our equation. This is really the same equation. This is just 2 times the one that we had at the end there. The two solutions that we came up with were e to the negative t, and we'll call that one y1. And then there's y2, which was e to the negative 2t. And so what we can do is I can verify that. And if you remember, verifying really just means we're going to prove that when we plug in one of these solutions into our differential equation, it makes it a true statement. So that means we want to be able to say the second derivative with respect to t of e to the negative t plus 3 times the first derivative with respect to t of e to the negative t plus 2 times e to the negative t is equal to 0. So if this is in fact a true statement, which we don't necessarily know right off the bat, then that means that y1 is a solution for our differential equation. So we can do the little bit of a calculus required here. Take the first derivative, the negative comes down. Second derivative, it comes down again, gives us just e to the negative t. This becomes 3 times negative e to the negative t plus 2 times e to the negative t. And the question is, does that in fact equal 0? And hopefully you can see that we have positive 1 e to the negative t minus 3 times e to the negative t plus 2 e to the negative t. And sure enough, this does check out. This is true. So that means y1 of t is a particular solution for the differential equation. Now notice I wrote it's a particular solution because it's not the only one. There are infinitely many. There's another one right here. And we can similarly show, there we go, I can spell. We can find that y2 is also a solution. And so both of these are particular solutions, and because both of them are particular solutions, that means that we know two values of y of t that make this differential equation true. But if we wanted to find the general solution, well, we don't really have a method for that, at least not yet. So note, using Maple, we can find the general solution. And so I'm going to hop over to Maple real quick, where I've actually already got the code typed in so we can verify what the general solution is. And if you notice, the general solution looks awfully familiar. It's something times e to the minus 2t, a constant times e to the minus 2t, plus another constant times e to the minus t. And so that should look pretty familiar to us. And of course, that looks familiar to us because those are the two particular solutions that we just got done proving are particular solutions. So using Maple, we find that the general solution is really just a constant multiple of our first, e to the negative t, plus a constant multiple of our second, e to the minus 2t. Now you'll notice e to the minus t, e to the minus 2t. I can reverse the order of these. It doesn't matter what I call the constant sitting in front of them. This is just so that it lines up with y1 and y2. And so we have here a constant times y1 and then another constant times y2. Right? So neither one of those are the general solution, but both of them together with constants in front of them is the general solution. So I'm going to add a little note down here and say we could also try to solve this second order differential equation by turning it into a system of first order. And we learned how to do that back in earlier in chapter 2, but unfortunately solving the system wasn't something that we could necessarily do analytically. We could manipulate it and take a look at the graph of it, but solving it analytically would have gotten us into trouble. Just as a frame of reference here, if this is my first order differential or my second order differential equation, my system would involve the one equation that we all know to begin with, which is dy dt is the same thing as v. So that's my one equation. And the other equation would be dv dt equals, and then I'd have to manipulate this guy and say that's dv dt right there. Second derivative of position is the first derivative of velocity, and then those two terms move to the other side. So this one would be negative 2y minus 3v. And this system right here, oops, sorry, let me scoot it up. That is the same thing as my second order differential equation, but just looking at it, how do you solve a system? How do you solve a system like that? And so we need a way to solve this system. And unfortunately, other than Maple right now, we really don't have one. But that's actually what we're going to develop in this section. So if you flip to the next page, oops, let me grab my next page here. If you flip to the next page, you can see sometimes systems are pretty easy for us to solve. And the easiest type of system to solve is one that's called a decoupled system. And so let me kind of make some notes on this here. The word decoupled, it looks and sounds pretty much like what it is. A decoupled system is one in which each differential equation in the system contains terms with only its own dependent variable. So for example, in this one, dx dt only contains terms with x, there's no y involved, and dy dt only contains terms with y, there's no x involved. So we can write this as it's some function of x, but only x, and this one is some other function of y, but only y. So that's what makes it decoupled. So the other thing that's worth noting is that when you look at this, you can probably, hopefully, very easily and quickly say that if x is 0, dx dt is 0, and if y is 0, then dy dt is 0. So just looking at this, we can tell that 0, 0 is an equilibrium point on the phase plane. And so that's the phase plane for x and y. Right? In other words, the origin of the phase plane, we expect it to be an equilibrium system. The only question, or the equilibrium point, the only question is, how does it behave everywhere else? What's the solution for this? And that's what we're going to do next. Because it turns out that because this is a decoupled system, we can treat each one of these equations separately. Since the dx dt doesn't depend on y and the dy dt doesn't depend on x, we can look at each one of them separately. And so for x, all we have to do is consider dx dt equals negative 2x, and what would its solution look like? And for y, all we have to do is consider what's the solution when dy dt equals negative y. And so for both of these, we can solve them, but it's worth noting that we're going to use, in both cases, the separation of variables. And that's easy stuff. We know how to do that. As a matter of fact, we didn't even have to write this out in any great detail since we've seen these equations so many times, these type of equations. This is exponential decay for both of them. So without much trouble, we should be able to say x of t is, okay, so that would be constant, some constant, call it c1 times e to the minus 2t. The 2, negative 2 coming from that constant, that proportionality constant there. And notice I put C1 here because that constant, this guy right here, is from the integration process. And there's going to be another one over here for our y of t, but that's a totally different integration, so that's going to be written as a different constant. So this one is e to the minus t. So we actually have two separate equations that we were able to find without much trouble. And it's worth noting that these two constants, C1 and C2, are coming from different integrations. So these are going to be different constants. All right, so a little bookkeeping there. So it turns out we just solved this system, and so that means we can write the system's solution is, well, it's just the x of t and the y of t equations that we just found. Now notice, because it's a system of differential equations, any solution would have to account for a solution for each one of those dependent variables, so an x of t and a y of t. Now we can write it this way and just say, oh, it's just grouped together like this. My x of t is just going to be c1 e to the minus 2t, and my y of t is just going to be c2 e to the minus t. Now you might be tempted to look at this and go, oh, okay, so though I can put them together. Well, they're technically the coordinates. You can think of it that way. This is the form of the solution called the scalar or parametric form. And that's because we're dealing with literally the x and y coordinates, and the parameterized version of the solution. Right? But if you can have a scalar form of a solution, then you probably guessed it, there is a matrix form of the solution as well. And the matrix form of the solution is going to be in the form of some kind of matrix. I'll write it with a boldface capital Y of t. And that's going to look something like this. There's going to be an x of t solution up top and a y of t solution in the bottom, and it's written like this as a matrix. And so that means my matrix solution would just be c1 e to the minus 2t up top and c2 e to the minus t on the bottom. And this is what we call the matrix, or scalar, or not scalar, vector form of the solution. Now the vector form of a solution is really handy because it predicts at any given moment in time what the x and the y components of your solution will be. But of course, that's just telling me the coordinates, x and y coordinates on the phase plane. So there's good information there for us. And so either way, whichever way you approach it, whether you think of it as a scalar or a vector, each way we can think of this as saying, as t approaches infinity, what's happening? What's going on? Well, as t approaches infinity here, the x and the y are both approaching 0, because as that upstairs approaches negative infinity, this thing just kind of shrinks away to nothing. Same thing happens down here. x and y both approach 0. And of course, for the parametric form, for the scalar form, that's just saying that the x-coordinate and the y-coordinate are going to approach 0 regardless of your C1 and C2, regardless of your initial condition. And down here in the matrix form, this is saying that your solution is approaching the 0, 0 vector, the column vector. In other words, it's approaching 0 length at no particular direction. So that's telling you you're winding up headed towards the origin. So on the phase plane, for the system, all solutions, I should say all solution curves, head toward the origin. So this is big news, because taken together with the fact that we knew the origin from up here, the origin is an equilibrium point. Now, not only do we know it's an equilibrium point, but everything's headed towards it. So we would expect our phase plane to look something like this, where this is x and this is y. We would expect that origin to be an equilibrium point, but everything kind of heading towards it. So we expect that kind of behavior. Oops, sorry. That means that we expect the origin will be a sink, what you and I would refer to as a sink before. So let's check it out. Let's verify this in Maple. Let's prove that that indeed is what happens. So here we are in Maple, and I'm going to do a DE plot, and I have to type in my equations. So you can either use the palette, or I'm used to typing in the code. So I'm going to say my differential equation dx dt equals, what was the equation again? Oh, I forgot. I have to grab my document to read it here. Negative 2 times x of t. And my differential equation for y of t is just negative y of t. So notice inside my first set of brackets are my equations. They're a group, they're a system, so I have to consider them as a system. And then after that, after the comma, the next thing I have to do is group together my dependent variables, and I have to put them in order, just like the equations were. So x of t and y of t. And then comes my independent variable, t. I'm just going to go from 0 to 2, nothing fancy. Remember, without an initial condition, the t variable doesn't actually play much of a role on your DE plot. And then window settings for x will go negative 5 to 5, and y is going to go negative 5 to 5. And so just standard, no initial conditions. This is what my DE plot looks like. And sure enough, we predict any place you start on the phase plane, all solutions head towards the origin. And we can test that. We can throw an initial condition in here and say, what happens if our initial condition was something like 0, 2, 2. So I would expect it to start at 2, 2, and then head towards the origin. And sure enough, that's what happens. Ugh, that ugly line color. Ugh. Line color equals blue. So it stands out a little bit more. Sure enough, it starts at 2, 2, and then heads down towards the origin. Notice it doesn't get there. It doesn't actually reach the origin. It's just headed towards the origin. If I play the clock further a little bit, from 0 to 3, I get a little bit closer. But notice it didn't go very far, but it's getting closer. If I want to show the curve going the other direction, I have to literally go backwards in time. And so if I enter any t value that's negative here, so from like negative 1 to 3, I see the curve go backwards in time from 2, 2. But that's the only way you can get that to happen. The only other thing that I wanted to show you real quick was this graph, this direction field that we see here. We can actually create that with a field plot command. And the field plot's a little bit more forgiving because we can just use the right-hand side of the equations and not listed as functions. So negative 2x comma negative y, and then we do our window settings. So x goes from negative 5 to 5, and y goes from negative 5 to 5. And we can see a field plot that shows us essentially the same information, but with the added bonus of seeing not just the direction, but the magnitude of those vectors, right? So remember, each one of those little red arrows, they're not all equal. Some of them are longer than others, and some of them are shorter than others, depending on how strong the field is at that point. And so the field plot shows us that. The only downside with the field plot, you can't include an initial condition. So, both of them together allow you to get a really good idea what's going on the phase plane. And so that ends this video. In the next video, we're going to take a look at a partially decoupled system.